Okay, so welcome back. We are now going to enter into the theory. So buckle up. We've got 6 pages to get through, but it's not that bad, and it actually makes a lot of sense once you go through it. So we're going to start off. We're going to be looking at initial value problems. So uh, these are the ones that typically run into where we're given some sort of initial condition, and there's some pretty cool stuff about them. So first off, before I jump into initial value problems, I wanted to address this linear equation part up here. So every one of the pieces of theory that we're going to be looking at from here on for this section is going to be linear equations. So we are not going to have any powers of y that are greater than 1 and no products of y. So there will be no y squared or y primes or any of that. All that is disallowed in this. So we are strictly sticking to y prime, y double prime, all that stuff. So here we go. Initial value problems. Turns out that if you write them kind of like, this is going to be theory too, so the notation is actually important. If I have something that looks like a sub n of x times the nth derivative of y with respect to x, something like that. Oops, my system is running a little slow there. Plus a sub n minus 1 times of x, the n minus 1th derivative of y with respect to x, dot, 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 all the way down to a sub 1 of x dy dx plus a naught of x y equals g of x, some function of x. Alrighty, so if I have it in the standard form, my differential equation, and I have initial conditions, my initial conditions are going to be things like y of x naught equals y naught, y prime of x naught equals y1, y double prime of x naught equals y2, dot, 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 all the way down to y n minus 1 of x sub 0, x naught, equals y sub n minus 1. So if I have initial conditions of every single one of the powers except for the leading derivative of y, so if I had a y to the fourth equation of fourth order linear, I would have all the way to y triple prime for my initial conditions. So let's say I have all of this. Then, here we go. Here comes the theorem. Let's do a sub n of x, a sub n minus 1 of x, comma, dot, 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 all the way down to a sub 1 of x and a naught of x and g of x. Okay, so all of my coefficients, and I say coefficients loosely because, as we've seen in the past, these aren't the traditional coefficients which are constant, but these are functions of x that are in front of our different derivatives of y. So function of x, function of x, function of x, function of x, and function of x. All these are functions of x. They can be just constants if that's what they are, that's totally fine, but they can also be any function of x that's well behaved. Alrighty, so you're not going to get crazy things like the 5/7 power of the sine of x or anything like that as your functions out here. But we're saying normal, well-behaved functions of x, including constants. We have all of these, and if they are, let them be continuous on interval I. Okay? So, whatever interval that we're looking at, all of these functions have to be continuous on that interval. And let, here we go, this is the big one, a sub n of x not equal 0 for every x in I. Okay? So, this leading coefficient, function of x out here in the front, no matter what x I plug into it, for the x's that are allowed in the interval, this cannot drop to 0. If this becomes a 0, then we wind up losing the order. We wind up this dropping out completely because it's a 0, and now we have an a sub n minus 1 order of differential equation. Does that make sense? So this cannot be 0. Whatever it is, for all the x's I can plug in on the interval, that can't go to 0, because then it reduces the order. Okay? So if we have all of this where they're all continuous and this never goes to 0 for any x I can throw into it, then here we go. If x equals x naught is any point in I, then here we go. A solution y of x of the IVP exists on I and is, here we go, unique. Okay, I wish I could like box that, put it in bullet points, and do all sorts of crazy colors around it. So what did we just say? We talked about what the preconditions had to be if x equals x naught, so the initial condition location, if that value is in any point that's inside that interval that this is defined over, then a solution of the IVP exists and is unique. We kind of already knew that it exists in most cases. That's kind of something we've been assuming that we can solve for y of x and everything will work out. But what we haven't done up till now is said it's unique. So it turns out when you have your initial condition and you solve your differential equation, then use your initial conditions to solve for all of your c's, we've been getting what we've been calling a particular solution. What we haven't nailed down up till now is that that particular solution is unique. There is no other solution. So when we've had a situation where we have had slightly different forms depending on how we handled our constant and where we decided to stop when we were simplifying things, every one of those versions had to be the same thing because there is only one equation that is a solution for that initial value problem. Okay? This really, out of the entire section, this is the big one, is that once we solve for our particular solution using the initial conditions, we have the solution. It is not one of many. It is that specific solution, and it is only that specific solution. So, bam. How do you like them apples? Kind of cool. So, if I have, let me clear this and do an example. Let's see. Clear. Gosh, I have such a hard time clearing the screen. I don't know why. So let's say that I have 3y triple prime plus 5y double prime minus y prime plus 7y equals 0. And I know that for my initial conditions, I have y of 1 equals 0, y prime of 1 equals 0, y double prime of 1 equals 0, okay? And that the solution, one of the solutions, if I have all these cases, this is where my y values are going to wind up 0. All of these values are going to be 0 if I'm at x equals 1. That implies that all of these terms, at x equals 1, these terms are all 0, which implies that the only solution I can have for this is going to be the trivial solution. So the trivial solution is just that y has to equal 0. Okay? If I nail down that this is the solution for x equals 1, x equals 1 is in the interval of solutions for this because this is from negative infinity to positive infinity. That's the interval that this is defined over. Then I can say, here we go, the trivial solution is the only solution that contains x equals 1. Boom. Isn't that just remarkable? So, because of the theorem that we had previously, once we have our initial conditions and we arrived on a solution using those initial conditions, that's the only one. So if you have your initial conditions and you wind up solving out and it has to be the trivial solution, that's it. You don't have to look any further. That is the only solution that contains those initial conditions. Isn't that wild? It's just stunning that that is the way it goes. And it will save you a lot of work and make your life very easy with that in mind. So let's do another example. What do you say? So let me just clear this and start fresh where we can get through it all on the same page. So here we go, clearing the screen. Okay, so we have y double prime minus 4y equals 12x. Okay, and we're going to be given the initial conditions of y at 0 equals 4 and y prime at 0 equals 1. Okay, so let's say that I have been given the solution as y equals 3e to the 2x plus e to the negative 2x minus 3x. Okay, how would I verify that that is a solution? Well, I would take the first derivative and then the second derivative, plug it in here, subtract 4 times the original, and it turns out you wind up with 12x equals x. Okay? Now, if this is a solution for this specific set of initial conditions, this is the only solution. This is unique. That means I don't have to look any further for another solution. That's it. There's no other. And I'm guaranteed that it exists. So even if I have a horrible situation, as long as the original things that I put up there, the requirements, the prereqs, are satisfied, there is a solution. It's just might be a messy one. But now that I've shown you this, what if I had done x squared y double prime minus 4y equals 12x? Okay? Now, and I had the same, I don't know what this one would equal. I haven't done this, but we're saying we're at the same location, some values here. Alrighty. So, if I have this for my system, now I don't have a unique solution. Why? Well, think back to those prerequisites that we had. Every one of the coefficients, if you will, the a sub n functions of x that are in front of my y terms, they all have to be continuous. No problem here. These are all continuous. And the leading coefficient, the leading function of x, cannot be 0 for a given x. But right here, x is 0. That will take this whole term and change it to a 0. So I can't be at that point guaranteed the uniqueness and existence of a solution. So be very careful, not that I'm going to try to trick you or anything, but in the wild, when you're looking at differential equations, make sure that your initial conditions don't wind up setting your leading term to 0. You're going to have a bad day if that happens. Alrighty, so that's that. And now we can move to the next thing, which is kind of cool. I hope you like that. That kind of puts the IVP to bed. So these are all IVPs, right? They're all located at the same location. Okay. Now let's look at boundary value problems. These are fun. I think I actually like these better in some cases. They're just more satisfying because you run into boundary value problems a lot in physics. So I guess it might just be I've seen a lot of them, so I like them. So what is a boundary value problem compared to an initial value problem? Well, boundary value problems don't take place at the same value. They have things like y at, I don't know, 1 equals 0 and y at pi equals 5. So we have different locations, the different x values that we're going to be plugging in. Okay, so just like I did before, we're going to have some kind of notation put out here. So a2 of x, second derivative of y with respect to x, plus a sub 1 of x times first derivative of y with respect to x, plus a naught of x times y equals g of x. And you know, we could extend it out to a sub n. We don't have to though. We're familiar with that, but this is a nice little sequence that kind of shows you what you can have. So let's say I have initial conditions of y at x equals a is equal to y naught, and y at x equals b is equal to y sub 1. Okay? Now, if I have this kind of setup, and I don't remember if these have to be continuous, but we'll just say that they need to be because it follows the same format as before. I'd have to look in the book for that. Not important. Actually, it is important, but I'm not going to dwell on it. So if I have a system kind of like I did before, but now I have boundary values where I've got the location of X is changing for each of my conditions, then I can have the following. BVPs have dun, 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 ready? Many, one, oh, that should be lowercase, none solutions. Okay? You do not get the unique existence for boundary value problems. Your boundary problem, that boundary value problem is going to either have a bunch of solutions, one solution only, or no solutions. Okay? So, unfortunately, we can't guarantee what we were able to with the initial value, but that's okay. Boundary values are kind of cool because of what you can do with them. Let me show you some examples. So if I have, let's say, x double prime plus 16x equals 0. Okay? And I know that my system, this right here, if I am adding the second derivative to 16 times the original expression and getting 0, I'm going to have some sines or cosines in here because after taking the derivative twice, they wind up being the negative of themselves. So my solution is going to look like x equals c1 cosine 4t plus c2 sine 4t. Y'all remember doing that? Hopefully. Um, let's say I have the boundary values, the initial conditions, or the boundary conditions, if you want. Let's say I have x of 0 equals 0 and x of pi over 2 equals 0. Okay? So what do I do with this? Well, I plug these boundary values into my solution and use that to solve, not my solution, into my solution. That's the correct way to say it. Use the resulting values to figure out what C1 and C2 need to be. Okay, so here we go. I'll plug in this 0 here. T is 0, and then that means X is 0. So for the very first one, X is going to be 0, and T is going to be 0. So this is going to be C1 cosine 0 plus C2 sine 0. Well, sine of 0 is 0, so that's the y value at radian measure 0, and this becomes a 1. So I wind up with C1 equals 0. Okay? So the next boundary condition is that my x value is 0 when t is pi over 2. But I also have that C1 is 0, so I can just eliminate this whole term. So I'm going to have x is 0, so 0 equals, I'm going to have C2 times sine of 4 times pi over 2, which is 2 pi, right? So 2 pi means sine of 2 pi is 0, right? So this means that 0 equals 0, okay? It doesn't matter what I do with my C2, C1, whatever, I wind up with a true statement. 0 equals 0. So this has really infinite number, but many solutions. It falls under that many category because I can plug anything I want in for C2 right now, and it's still going to hold true. So that's how you handle this type of situation where you have boundary conditions that result in kind of a tautology. If you've taken math logic, tautology is a statement that's always true. And 0 equals 0 is pretty much a true statement. So that's the first look at it. Now let's look at the boundary conditions of Let's do x at 0 is 0, and x of pi over 8 equals 0. Okay? Well, the first condition is exactly the same, so I'm going to wind up with C1 equal to 0. So I'm just going to jump straight into the second line where I'm going to be solving for C2. So I'm going to have 0 equals C2 times sine of, well, 4 times pi over 8 is pi over 2. Okay? So I wind up with sine of pi over 2 is 1. So I'll wind up with C2 equal 0. So C1 is equal to 0 and C2 is equal to 0. That has one solution. We are locked in. Both of the initial conditions have values. Not the initial condition, the constants have values that are assigned. This only works for C1 equals 0 and C2 equals 0, which really winds up being, for the whole thing, is going to just be x equals 0, which is kind of odd. But yeah, that's okay because everything else drops out. C1 0, C2 0, x equals 0. Hooray. So I can fit in the last one right here, I think. Now let's look at the boundary condition of, let's go with x at 0 equals 0, and x of pi over 2 equals 1. Okay, so I wind up with my C1 having to be 0 from this one, so I wind up with the same thing. But now I'm going to start off, I've got this initial condition, this boundary value to plug in. So 1 equals C2 times the sine of, well, 4 times pi over 2 again is 2 pi, and sine of 2 pi is 0. So I'll wind up with 1 equals 0. That is a contradiction, therefore these boundary values have no solution. And there you have it. Many solutions, one solution, no solution. It all depends on what your boundary values are for your boundary conditions. That's it. That's what we were talking about when you don't have a unique solution for boundary value problems. You only have that possibility of many, one, or none. Alrighty. That was the very first full page of stuff, so we are moving on. 5 to go. So let's clear this and start on the next section. Okay, if I can clear this screen. It's being mean. There we go. Alrighty. So here we go. The next little bit to take care of is something you're going to absolutely love. I'm going to go kind of quick with this. A sub n of x, the nth derivative of y, dot plus dot 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 all the way down to a sub 1 of x dy dx plus a naught of x y equals 0. If you have your differential equation done out in standard form and the g of x term over here is 0, this differential equation is called homogeneous. But wait, I can hear you saying, we've already used homogeneous. We used homogeneous back in 2.5 when we had that whole, oh gosh, what was it? It was m of tx, ty is equal to t to some alpha times m of x and y. You remember that? We had that kind of situation in our equation. We said that was homogeneous. Well, we're meaning something completely different with this. So just, I know, This is not going to be the only time, as you've seen already, and especially when you get to part 2, where DE uses the same term for different things. So from now on, I will never refer to section 2.5 and when I'm saying the word homogeneous. Okay? Homogeneous only means that the g of x is 0. And if g of x is not equal to 0, then I get to call that non-homogeneous. Very unsatisfying, to be honest. I wish it had its own name, but it doesn't. It's just non-homogeneous. Okay? So this is just, like I said, this is some theory that is going on, some preliminary stuff that needs to be taken care of before we dive into chapter 4. But it's this right here is just terminology. That's it. So if it's equal to 0, it's homogeneous. If it's not equal to 0, it's non-homogeneous. Okay? So now that we got that out of the way, let's have some fun. I'm going to clear this so I can have a nice clean slate for what's coming up, because this is really nice. This is one of my favorite things that we're going to do for the entire semester. I absolutely love this. So we are going to introduce something called the differential operator, D. Okay? The differential operator D. What is D? Well, D is going to be a kind of a shorthand notation for a derivative. As an example, if I do dy dx, I can now rewrite that as just capital D y. Okay? And I can say things like capital D cosine 4x is just negative 4 sine 4x. Right? I could do, here you go, you ready? D squared of maybe, oh gosh, I don't know. I'm drawing a complete blank. I'll do 3x to the 5th. This is the second derivative of whatever the argument is. So that would be, first derivative would be 15x to the 4th, and second derivative would be 60x cubed. This would be the answer for what d squared of 3x to the 5th would be. Okay? So we can now take a lot, and we're not going to do it all the time, but in a lot of cases, we're going to eliminate doing that really tedious to write notation, and we're going to replace it with just a nice big capital D. It is way, 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 way cleaner when we deal with certain types of expressions. Now, here's the kicker, okay? We can actually make polynomials of this operator, the differential operator. So let's say I have y double prime plus 5y prime plus 6y equals, I guess, 5x minus 3. Okay? I can now rewrite this as, here we go, you're going to love this, d squared plus 5d plus 6 times y equals 5x minus 3. That is so cool. I love that. This also, I'm hoping, look carefully at this. You notice anything odd about d squared plus 5d plus 6? Yeah, we're going to be factoring differentials. We're going to do things like d plus 3 times d plus 2 times y. Oh, Sorry, I shouldn't get that excited about this, but this is really cool. We're going to take this notation and run with it in some of the sections that are coming up. And actually, you'll see it from here on for the rest of your life. You will see occasionally the differential operator used. It's just a very compact, neat way to represent derivatives. So I hope you're excited about seeing it. I hope I saw a lot of y'all were just like, what? Because I hope you did. That's what I did the first time I saw this. This can't be right, but it makes life so easy with some of our problems that are coming up. So store this one away. We're going to be using it. And it goes without saying, although I need to say it, that the differential operator can, based on what I just did right here, you can form linear combinations of it. You can do all sorts of stuff. Notice that there's a 5 out front of this differential operator right here, 5D. So you can basically form polynomials with it. So just we've already done it, but just know that that is completely allowed. There's a nice little proof in 4.1 about it if you want to look at it. I personally don't want to go through it, but if you want to verify for yourself that you can do this kind of thing, the proof is in there. Just I don't want to bog down on it too much. Alrighty, so here we go. That right there, believe it or not, is most of page 2. So now we can go to page 3. Alrighty, so page 3 of the theory. Dun, dun, dun. Let's knock this out. So page 3 says that, here we go. And actually have, oh no, not my brush size way up. Let me knock that back down to something that makes sense. Okay, so let's say we have a set of functions. And we're going to call them f1 of x, f2 of x, f3 dot 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 all the way down to f sub n of x. Let's say that I have this set of functions. I can say that this set of functions is linearly dependent on I, I've got to put that interval in there, if there exists, here we go, constants C1, C2, dot dot dot, all the way to C sub n, not all 0, okay, such that C1 times f1 of x plus C2 times f2 of x plus dot 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 C sub n times fn of x equals 0 for every x in, oh wait, yeah, I, that's correct. I have to state that. Now, what on earth does this mean? Well, this is actually a pretty big statement right here. So this says if I have a set of functions and I can take constants, C1, C2, Cn, multiply the functions by these constants and wind up with a 0 over here for every x and I, then these functions are linearly dependent. Okay, what does that really mean? Well, what that really means is, let's say I have, I'm making this up, so boy, I hope I don't mess this up. F1 of x equals x plus 2. F2 of x equals x minus 2. And F3 of x equals x. Okay? Now, if I do F1 of x plus F2 of x minus 2 of F3 of x, I'm going to get a 0. X plus 2 plus x minus 2 is just going to be 2x. And then minus 2 times x minus 2x equals 0. So that means that these functions are linearly dependent. Okay? So that is, it may seem like kind of an odd thing to say, but we are going to require this to not occur in what we're going to be doing. So if I can put constants in front of my functions, a 1 here, a 1 here, a negative 2 here, and add them all together in some linear combination and get 0, it is linearly dependent. Okay? Now, the opposite side of that, the flip side, is going to be, let's see. Oh gosh, do I really want to write all that out? The flip side is if I do C1 F1 of x plus dot dot dot. So I've got these constants that are in front of Fn of x. And it equals 0 only when C1 is equal to C2 is equal to C sub n. All of them are 0. Then this is linearly independent. So if I can make this equal to 0, but only by making all the coefficients 0, then it's linearly independent. It's kind of like the flip side of what we just did. This one's kind of like, I don't really take great satisfaction. I like the previous one a lot better. So it's actually going to be a big, big deal. So we need some way of coming up with whether something is linearly dependent or linearly independent without having to do guesswork by doing all the adding multiples of the functions and trying to wind up with 0. So enter, dun 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 dun. You ready? I'm going to clear for dramatic effect. Enter the Wronskian. If you've taken linear algebra, you've already seen this, but if you haven't, you may not have. So what is the Wronskian? So the Wronskian is set up like follows. The Wronskian of f1, f2, dot, 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 f sub n is equal to, here we go, a matrix, okay? f1, f2, dot, 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 fn, f1 prime, f2 prime, dot, 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 fn prime, dot, 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 all the way down to f1 to the n minus 1th derivative, f2 to the n minus 1th derivative, dot, 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 f sub n to the n minus 1th derivative. Alrighty, so we're going to find the determinant of this matrix, which is composed of the original functions, and then each row is a subsequent derivative all the way to this value minus 1. So if I have 3 functions, I'm going to go down to the second derivative. Okay? So if the determinant of this, I'll even write it right here, if the determinant of the Wronskian, dot, 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 f sub n, if the determinant is not equal to 0 for all x in I, f1, f2, f sub n are linearly independent. Okay? So the way I can tell if functions are linearly independent or dependent is by running the Wronskian. So I set this up. Let me do that where it's easier to see. I set this up right here where I make the matrix. I had to list my functions across in the first row, and I list their derivatives across in the second row, all the way down to the n minus 1 derivative based on the number of functions I have that goes out to n. When I take that determinant, I then check to see if it is ever equal to 0 for any x that I can throw that's inside the interval. If it does not equal 0 for every x I can throw at it in the interval, then it's linearly independent. We have locked down the f1, f2, all the way up to f sub n are linearly independent. Okay? So we're going to start off with, let's see here. Oh, let's see. What did I have before? I had f1 is x plus 2. This is probably not going to be a very interesting example. I'm already looking at it going, no, you shouldn't do this, but I'll do it anyways. I've already written it out. And then f sub 3 is x. Well, let's see if it's linearly dependent according to the Wronskian. So Wronskian of all this, f1, f2, and f3 is going to equal, well, we're going to have the original functions, x plus 2, x plus 1, x minus 2. I'm looking ahead and going, oh yeah, you really shouldn't do this. This is a terrible example. First derivative is going to be 1, 1, 1. Second derivative is going to be 0, 0, 0. I can already tell that determinant is equal to 0 because of all these factors down here. So since it's equal to 0, for every x I can throw in it, it is definitely linearly dependent. So these are linearly dependent. Okay, but let's do an actual example that's in the book, so it'll be a little bit more satisfying. Alrighty, this is going to look so hideous, but you're going to love it. So my example is going to be, I have x squared y double prime plus 7xy prime plus 13y equals 0. Okay, and I have the following solutions. So the solutions are going to be y1 of x is going to equal cosine of 2 times the natural log of x over x cubed, and y2 of x, the second solution, is going to be sine of 2 times the natural log of x over x cubed. Question is, are these solutions linearly independent? Well, we have to set up the Wronskian. So the Wronskian is going to look like, and I'm just going to do, I guess I can do y1, y2, and just be happy with that. Well, it's going to look like this. Here we go. Cosine 2 natural log of x over x cubed sine of 2 natural log of x over x cubed. Then their derivatives, which happen to be, here we go. Oh boy. Negative 2x squared times the sine of 2 times the natural log of x minus 3x squared times cosine of 2 natural log of x over x to the sixth. And then for this derivative, it's going to be positive 2x squared times cosine of 2 natural log of x minus 3x squared sine 2 natural log of x over x to the sixth. So let's just take the determinant of this and see if it equals 0. Alrighty? So one way would be to take the actual determinant, multiply this times this, and then subtract this times this, get some sort of hideous expression, and then try to figure out if that's ever equal to 0 for any x. But since I know it has to hold for every x, what I could do, let me get a little room right here, is just say, well, let's try it for x equals 1. Let's plug that in first and then do the determinant. Well, if I choose x equals 1, the natural log of x's, which would be natural log of 1, is a 0. So this becomes really, really easy. Cosine of 0 is a 1 over 1. That's nice. Sine of 0 is a 0 over a 1. Down here, I'm going to get negative 2 times 0, and then negative 3 times 1 over 1. So this whole thing is going to wind up being a negative 3 over 1. Here I'm going to get positive 2 over 1. So I'll wind up with, when the dust settles, the determinant of 1, 0, negative 3, 2. Okay? 1 times 2 is 2. Minus 3 times 0 is 0. 2. Is that 0? No, that is not equal to 0. So I know that they are linearly independent for x equals 1. And I'm trying to think, can you say that for all? Because you really didn't try all x values. They are linear independent if it's not equal to 0 for all x in I. Okay, so if it is not equal to 0 for all x in I, they are linearly independent. So that would mean that it is not for all x in there. But can you say that for sure? Let me do a quick check while y'all wait and think about that, because I want to make sure that I get that one right, because the Wronskian is extremely important. Okay. Oh, it will hold for all of them. Yep. All we had to do was disprove it for x equals 1, and that the interval that contains x equals 1, they are linearly independent for every value that you can throw in there. Oh, that's nice. That's very nice. That's what I was hoping I would find. Wanted to make sure. So, as a recap, what have we done? We have now developed a tool to be able to tell if our solutions that we get are linearly independent. That's going to be very important in the things that follow. So how do you do it? You set up the Wronskian, you run the determinant. If you need to, you can actually plug in a value in for x to simplify your determinant, and then see if it equals 0. If it equals 0, you're out of luck. If it doesn't equal 0, you're good. Well, when I say you're out of luck, if it equals 0, they're dependent. If it's not equal to 0, they're independent. So there you go. Alrighty. So this is at the halfway mark for the theory. So I'm going to give y'all homework and call this good so that you don't get too swamped. This is the way I do it when I teach the normal class. So homework and this from section 4.1, is going to be numbers 3, 13, 15, 19, and 21. Okay? So let's see. I want to open this up, make sure that I can give you instructions on this because I don't remember exactly what all those are. Alrighty. So for number 3, you're going to be using the initial conditions in order to find the particular solution. And when it says find a member of the family that is a solution, it's asking for the particular solution. So just use your initial conditions in 3 to find the particular solution to eliminate your C1 and your C2. And then in number 13, you're going to be doing the same thing, but now you're going to be dealing with boundary values. So when you solve out, once you plug your initial conditions in, your boundary values in, when you solve it, just state to the side if it has many solutions, one solution, or no solutions. Okay? And then 15, 19, and 21 are all Wronskians. So use the Wronskian to tell if something is linearly independent. That is a really good set of homework, so I hope you enjoy it, and I will see you later. Have a good one. Bye-bye.